This is a lesson on interference in thin films in the university physics unit of light in general, wave nature of light. And we're piggybacking this lesson on what was understood of interference of light. This was started with interference of waves in physics 2 material. And the largest thing I want to remind you from that material is the constructive and destructive interference when I add two waves. What we look at is a path length difference. You can see a path length difference here. And again, we're going to remember that a path length difference for constructive interference is m times a lambda. We get a whole wavelength shift one way or another. A phase angle, a phase shift of 360 or negative 360, we're looking for a whole wavelength shift, as opposed to destructive interference where we get a half a wavelength shift, a phase difference of 180 one direction or another direction, right? So that the troughs and the peaks line up on each other and cancel out to zero like we're seeing in that picture. So when we're looking at thin film interference, we're going to take two rays and let them interfere. The origin of these two rays is when I have incident light onto a medium from one medium to another. You can see the N1 and N2. From one medium at the surface, that first surface here, this is the first surface here. This is what we call ray 1, and that ray 1, typically what we're seeing up here, ray 1, is if that N2, if that second medium is more dense than that first medium, then we're going to get a phase shift. We're going to see a shift of 180 degrees. And we're going to call that, again, a half a wavelength. And I have this picture up here. This is more of a mechanical, a physical wave, if you think about a wave on a rope. If you attach it to a wall and you send a wave down that rope, when it gets to that wall, it actually reflects at 180 degrees. And so that is the same situation that we're looking at here with the electromagnetic wave, is that we get this 180 degree shift upon reflection at a more dense surface. Okay. So ray 1, typically when we set up problems, when you look at problems at this level, the first medium is going to be less dense than the second medium, so we will get this shift of half a wavelength at that first surface. Sometimes it might be another situation where you're looking if N2 is less than N1 and you get a 0 in that case. All right, so that's ray 1, and remember we're interfering two waves, so we have to look at the total phase shift for both of those waves when they meet up. So when I look at ray 2, there's two contributions to ray 2. Ray 2, definitely what you see down here at B, right, is that B down here, I called them A and B. I'm looking at B first. When you get down to this second surface down here, because N2 and N3 are different, it depends on if N3 is denser than N2, like I talked about with ray 1. If N3 is denser than N2, then you will get a shift of half a wavelength. If it goes from, like, a situation might be air, soap, air, like if I have a soapy thin film, right, there's air on one side, air on the other, then that N3 is less than N2 and I would get a 0 phase shift at that interface. All right, so you need to be evaluating your N values, your indices of refraction for at each different interface to determine if there's a phase shift because of that. I'm going to go back here to A, and you can see that I've labeled that on the picture here. A here is due to this thickness, and you've seen some problems already where we've looked at a phase shift due to a thickness, because when a light wave is within that medium, it's going to change wavelength, right? I have that equation up here. It changes wavelength, and we're going to get a shift in wavelength because of that difference in wavelength. And actually, how we count that up is just, it's going to be like a 2t in there, 2 times the thickness. And I want to remind you, as we're looking at these phase shifts, this is delta 1 for the first wave. This is delta 2 for the second wave. These deltas, if you're noticing, they're in lambdas or thicknesses. These are both in meters. This is technically a phase shift in meters. This is a delta L, meters. Not M number, but M meters, okay? So when I look at the total shift, notice that we're going to look at the total shift with those two rays, right? We're going to add the shift up of those two rays and determine if it's destructive or constructive interference. So what we call this in the physics world is a delta-delta. One of the few places that I see a delta-delta, we're used to the delta representing a change, and we're also used to a delta being a difference. So we're looking at the difference of the difference. So there's a phase difference for ray 1, a phase difference for ray 2. We're going to add those together. This is for ray 1, delta 1. You're going to do that check at that first interface. Are those two indices refraction? What is their relative magnitude to one another? And then we're going to do the phase shift for the second wave, delta 2. There is a reflection at the bottom and it goes through that thickness. So that's the total delta-delta for the two waves. And if you want constructive interference, we're going to set that equal to m lambda. If you want destructive interference, we're going to set that equal to m plus a half lambda, like we have for prior interference problems. Okay, so I've moved through that. Take notes on it, right? And try to process it. But I think moving on to a problem where we have an example is going to be a good way to practice applying these concepts, and then setting up a problem to solve. And what I've done here is I've solved this problem before, and I just went through and I deleted the work. And so we're going to step through how I solved this problem. A layer of acetone, a thin film of acetone, and it gives the N value for that acetone. You can see I labeled it down here in the diagram or in the sketch down here. Lies on top of glass. So we have acetone and glass down here. Above the film of acetone is air, just to be clear. And so I put those N's in here as well. And remember when I was talking about when I look at the phase shift, I'm paying particular attention to those different N values, which one is denser and which one's not, okay? It says white light is incident normal to the film. So this is white light. We're just going to assume that there's all of the colors in there and they're all going to interfere with each other. I'm going to pin this in here at this point. Notice the eye is catching both those rays at once. In this picture, we exaggerate the distance between those two waves so that you can keep it clear which wave we're looking at. But when those waves actually come off of a surface, and remember there's billions of them, right? It's white light. There's rays everywhere. Even though these two rays are separate and drawn not on each other in this sketch, what actually happens is they are on top of each other and they do interfere with one another. And you can even just shoot light straight down, right? And then you wouldn't even have any angle to worry about. So I just wanted to cover that point while I was in here and just let you know that even though they're separate, they are interfering. In the reflections, fully destructive interference occurs at 660 nanometers and fully constructive interference occurs for 770 nanometers. It says, what is the smallest possible thickness of the acetone film? Hint. Make a list of the possible thicknesses to fulfill each of the two conditions and then look for the thickness that appears in both lists. So we get a hint on this problem. What I'm going to note here is we're going to walk through determining our delta-delta for these two waves. Okay, we're given a situation where there's fully constructive and fully destructive interference, so we're going to have to explore both those situations. So if I go for my delta-delta, I can set it equal to m lambda or m plus a half lambda and go from there. So let's do some analysis on these different rays. Let's look at ray 1. Ray 1 here, I'm going to notice at this purple point of reflection between those two surfaces, since N2, since the acetone index of refraction is greater than the air index of refraction, we're going to get a half a wavelength shift at that first interface, just due to reflection, okay? At that second interface, we are also going to get a shift due to reflection because the glass has a larger index of refraction than the acetone. So we're going to get another half a wavelength there. So we have 2 half wavelengths. If you're keeping track at home, 2 half wavelengths adds up to constructive interference, right? A whole wavelength. So let me put that in the equation here in a second. And then don't forget also we're going to get a phase shift because that light goes through that layer of acetone, and that's what we're looking for, right? Is that thickness. What is the possible thickness? So when we look at this, we're going to have a possible shift due to the thickness. We know that that's equal to n number of wavelengths, right? And so that's how we get our delta-delta equation. So when I write out my delta-delta equation, I'm going to take my delta 1. So right here is my delta 1. I'm going to add my delta 2, which has 2 components, right? This one and this one. This is my delta 2. I'm going to take those and add those up. So there's the first one, delta 1. I'm going to add on delta 2. Again, a half of a wavelength plus a half of a wavelength. That adds up to constructive interference. That's a whole wavelength, 1 lambda. And so that's constructive. So I'm just going to take that out of the equation. I'm not going to leave it in there. If I know it already adds up to constructive interference, I'm just going to let this equal 2t. Right? That 1 lambda results in constructive. So any interference I get is due to that thickness of the acetone in there, okay? So 2t, and we're going to call that the phase shift, the delta-delta for this problem. That's the delta-delta for this problem. Path length difference. Okay, that is the path length difference. We're going to set that equal to m lambda or m plus a half lambda. So let me get that going. Destructive interference is when I get m plus a half lambda. Constructive interference is when I set that path length difference equal to m lambda. And note also in here, note this little n in here, because we're within that acetone, we have to consider that that wavelength is shifting in that acetone, right? N value or lambda n is lambda naught divided by the n value. So we're going to have to take that and put that into the equation. So I'm going to go ahead and put that in there. I think I may do some algebra, right? Do you all see that algebra in there? So this is the lambda naught over n. There, lambda naught over n. So I'm going to look at the destructive interference happens for the 660 nanometer light, so that's down there. The constructive interference happens for the 770 nanometer light, so that's what I put down here in these equations, 660 and 770. I went through and I calculated all the different thicknesses that destructive interference happens for 660 and constructive interference happens for the 770. And when I look at these numbers, there's all the calculations. I started with m equals 0. Notice with destructive interference, I can start with m equals 0. I cannot start with m equals 0 for the constructive interference because that's a thickness of 0. That's not interesting. We want a non-zero thickness. So when I go through here, I kept calculating M1, M2, M2, M3, M3 I get here, and I notice that, oh, look at that. Make a list of the possible thicknesses of each condition and look for the thickness that appears in both lists. So when I get to 924, you all see M3 for destructive at 924, and M3 for constructive at 924. So that is going to be the thickness where fully constructive interference happens for this one wavelength and constructive happens for the other wavelength. So that's true for both. That's going to be our answer for the problem. What I wanted to make note and kind of wrap up for this video is the procedure to go through to figure out that path length difference, right? Because you saw this path length difference. That's the key to being able to move to destructive or constructive interference, is figuring out that path length difference. I see a lot of students guess and struggle with thin films because they've not routinized that process, that algorithm of going through each different, right? So if I highlight this on the slide, you need to figure out the path length difference for the first wave, which is just a single contribution due to the reflection at the first surface. You need to figure out the two contributions due to the second wave, where you have a reflection and also that thickness that you're moving through. And then that, when you add those two together, you'll get a delta delta. If you had left the 2t plus 1 lambda on there and set that equal to either m lambda or m plus a half lambda, I don't think you would have went wrong, because you just subtract, right, minus 1 lambda on both sides. But I think that means you would have had adjusted your m values. So watch out. A lot of times you'll see in a problem what's the smallest. Notice that there was in here it says what's the smallest possible thickness. That just means go with the smallest m value that works. Okay, so that's my tip on that one. Just a quick video here. I hope you enjoyed it, and good luck with your problem solving.